Okay, this is for Unit 5, and this is the day on cross-sections. So our goal today is to be able to find the volume, but unlike previously when we had a volume that was created by revolving around an axis or some line, we're going to find the volume by cross-sections. So what I kind of try to do is if you had some sort of a solid and we were trying to find the volume of it, the technique here is going to be more similar to if you were, almost imagine like you were at the deli and they were slicing something, and at the deli, if you sliced this, the bottom here would be a circle, right? So if you slice this, each piece would be a circle. And what we're going to do is find the area of each circle and then add them all together. And that's actually going to be integration. But that's kind of the idea here, is that you're taking this solid, you're cutting it up into these cross sections, and then you're kind of adding them all up to make it into 3D. And because it is related to the area there, whatever the area of the base is, in this case it happened to be a circle on this figure, but we can do bases that are all different shapes. So you need to remind yourself of all your area formulas. So obviously the area of a square is side squared. An isosceles right triangle, we've got base times height over 2. Rectangle and circle, those should be very familiar to you. And then semicircle and quarter circle, okay? The only one that's a little bit tricky is this equilateral triangle, and if you needed to, you can derive that formula. I have kind of the little trick here to derive it using the special triangles, but or you could just memorize that formula. That one's not used as often, but just in case it pops up, you can be ready. So notice here with the volume by cross sections, we can integrate with respect to x or with respect to y. Depending on what it'll tell you in the problem whether your cross-section is perpendicular to the x-axis or perpendicular to the y-axis. They will tell you in the problem. And so our volume formula, we're going to integrate from left to right here of the area. So we're integrating the area, and that should make sense because, again, we're going from the area and then kind of giving it that extra dimension. We're adding all those areas together, and that's where we get that integral. Remember, your integral, that's repeated addition, so that part should make sense there. Some notable differences between this formula and the formula from volume in the previous sections when we did discs and washers, you might notice that there's not a pi in this formula, which should make sense because remember in the previous we got that pi because we were spinning around an x-axis or some line or something like that, and that's where the pi came from. This time we're not spinning in a circle, so it stands to reason that that pi is not there. The only time a pi is going to show up in a cross-section problem is if your cross-section happened to be a circle, the different shapes. Okay, so we've got our formulas here, and we're going to go ahead and get started on the first example. Okay, so we've got example 1 right here, and what we got here, it says find the volume of a solid who's bounded by the various graphs. So I have y equals x squared minus 1 is this parabola, and then I have the line, right? This has a y-intercept of 1, slope of 1. So we've got this, and then it says cross sections perpendicular to the x-axis. So basically what that means is imagine, this area here is this kind of chunk, but what we're doing, and I'm using a post-it here, it's hard to see, but basically it says that we are going to cut it. If this was the deli slicer, we're going to come in, and this is just a rectangular post-it, and it's saying that perpendicular to the x. So if I was to kind of hold it just like this, okay, this would be one cross-section. So each cross-section you can see is a rectangle. And then what we're going to do basically is they're saying if there was, a million of these post-its all cut, I didn't obviously cut them all to the appropriate size, but they're going to kind of stack them up from here to here, one there, one there, one there, one there, all the way to the end. And obviously the width of that rectangle is going to vary, okay? But they're saying if you stacked those up with a whole bunch of rectangles, then you calculated the area of each one and added them, what would the volume of that solid be that was produced? So it tells me here that all the rectangles are of height 5, okay? But you could tell that the width of the rectangle right here is going to be different than if I put a rectangle, further to either side, right? So these two rectangles you could see are, not the exact same width. But this rectangle, you know, that one would fit right about there, and this rectangle would be here. They're still the exact same height, okay? But the width of each rectangle is going to change. So how would we calculate that width? Okay, we're going to need to think about that. And then we are also, sorry, this intersects right at 0. We're also going to need to figure out these points of intersection here. We're going to need to get the bounds of integration. So usually what I do is I kind of figure out the area piece first, and then I put it into the volume formula. So I'm just going to calculate my points of intersection, because those are going to be needed for the bounds of integration. So I want to know, when does this parabola equal the line? And so I've got x squared minus 1. When does that equal x plus 1? And I'm going to move everything to the left-hand side. So I've got x squared minus x minus 2 equals 0. And you can factor that, x minus 2, x plus 1. And then you would see that those POIs, so right here would be negative 1, and then right here would be 2. Okay, so that's a 2. Okay, so I know that when I do my volume formula, okay, I'm going to be integrating from negative 1 to 2, and then I need to integrate the area. So I'm going to kind of go up here and say, all right, well, what is the area of each rectangle? Well, the area of each rectangle is going to vary, because the area for a rectangle is going to be, you know, the height times base, or base times height. But why did I want to say the height first? So hopefully you'd agree that the area is height multiplied by the base. In this particular example, it told me that the height is going to be 5 every single time. So in this example, it's going to be 5 times the base. Well, the length of the base is going to be determined, and it's going to vary, right? We said that over here, you know, the base was going to be that long, but if I have the, you know, right here, if I was doing this one here, then this base is a different. So how do you figure out that base? Well, going back to when we did area before, we thought of it as top minus bottom. So this length right here that I dropped in, that length is going to be the length of the base, and we can calculate that by doing this curve, which is the line, minus the bottom curve is, you know, determined by that parabola. So here it's going to be x plus 1, that's the line, minus parentheses the parabola. So that's that x squared minus 1. Okay? And then we can obviously use a little algebra to clean that up. So, you know, distribute your negative there. So then you've got 5, and then we've got negative x squared plus x plus 2 once you distribute that negative and combine like terms. Okay. So now we can go ahead and take this, right, because the volume is the integral of the area. So we're going to take this and put it right here. And then we'll talk about some integral properties. Remember, with an integral property, you are allowed to factor out any constants. And I'm going to integrate this with respect to x, because it said that we are perpendicular to the x-axis. Okay, so that's going to be a dx there. I'm going to take this 5, pop it out front, because that's going to make my math just a little bit easier. So I'm going to say 5. We're going to integrate from negative 1 to 2. Okay, and then you can just do your integration. Okay, that's still dx. Okay, so now we're ready for the calculus part. We're actually going to integrate now. So add 1 to the exponent, divide by that number. Add 1 to the exponent, divide by that number. So that 5 just comes down, and you get negative x cubed over 3 plus x squared over 2 plus 2x. And we're going to evaluate that from negative 1 to 2. And then from there, it's just applying your fundamental theorem of calculus. So your fundamental theorem of calculus says you take the 2, you plug it in, minus what you get when you plug in the bottom number. And again, that 5 just kind of comes and goes for the ride. So you've got 5, And then I'll do it in parentheses here. So you've got, that's going to be negative 8 over 3 plus 4 over 2. Oh, that's 2, but plus 4 minus what you get when you plug in negative 1. So a negative cubed is negative, but then it's a negative there, so then it's a positive, but it's in parentheses, so you get a 1/3 plus 1/2 and a minus 2, close parentheses. And then here it's just death by fractions, so you can distribute this. I would kind of combine some like terms here. I don't have really a lot of room, but that's going to end up giving you 45 over 2. You can kind of go through those fractions and get that, but that's your answer for that one. So the volume would be that in, you know, whatever units you are given. Okay, in part B, we're going to be using the same graph, but we are now going to be finding the cross-section with an equilateral triangle. So what does that look like? What does that mean? So I had some equilateral triangles here, and so I have kind of, you know, two different, they're not perfect because I just cut them out, but the idea then is instead of using those rectangles like we were before, so remember we had a rectangle and those were our cross-sections, now we're using equilateral triangles. So we're saying, okay, well, the equilateral triangle, you know, there'd be one here, and then the equilateral triangle that fit, you know, there, those are going to be two different sizes, okay? So what we're doing is we're finding the area of a whole bunch, like a million of these things, kind of lined up, and they're going to be kind of stacked next to each other. And the idea is that if we find the area of each one and then add them all together, that's what's going to go ahead and give me the volume. So, again, we already have our points of intersection from previous, but you know, would have to find those if needed. And then we start off with our area. So we need to figure out the area of the cross-section that they're requesting. So here they were asking for an equilateral triangle, and I know from the first page there that the formula for equilateral triangles is square root of 3 over 4 base squared or side squared, or yeah, the base squared. Okay, so in this example, that's going to be radical 3 over 4. That part's the same, but then what's guiding the base? Like this measurement here isn't going to be the same for each equilateral triangle. We saw that in the two examples that I had showed you. They're not all the same. Well, it's going to be guided by whatever this line is minus that. So it's going to be that same thing. It's going to be negative x squared, okay? Oh, I combined them. So you're really going to have this minus that, okay? So if you did this minus that bottom curve, right? Top minus bottom, that's how you're going to get it. So if you distribute this negative, you get a negative x squared. You distribute that, you're going to get a 1 plus 1 is 2, and then a positive x squared there. So just like before. And then it was base squared, so this thing needs to be squared. So now you take that and drop it into the volume formula. So the volume, there's no pi with a cross-section unless your cross-section has to do the circle. So we're going to integrate, and we're still going to integrate from negative 1 to 2 because we're just using the same graph as example A. And now this time, though, we have this is what goes in there. Very similarly, we can take that radical 3 over 4 and pull it outside so that we're only left to integrate this negative x squared plus x plus 2 quantity squared, and we're integrating that with respect to x. Okay, so since this was a calculator one, this one, it would just be kind of a pain if you had to FOIL that out and everything. So you would use Math 9 on your calculator. Just be very cautious if you use Math 9. You still have that radical 3 over 4 out front. So you've got radical 3 over 4, and then when you use Math 9, my calculator got 8.1. And then don't forget to multiply that. So I got something to the effect of 3.507. And again, we round to 3 decimals because that's the AP rounding standard. Okay? All right, so then if we took a look with a square, so we're kind of changing the shape again. So we started with the rectangle, then we went to the equilateral triangle, and now they're saying, I want each cross-section to be a square. So if you went over here, like, this square looks like it would fit right about there. And we're just going to keep doing these squares. So the formula for the area of a square is side times side, or side squared. Well, each square is going to have a different side length because, the square that you drop in right here is going to be bigger than the square you drop in, really close to the edge there. So that base of the square is determined by this line minus the parabola again. And you kind of see this very familiar thing. So we have area of the square. That's going to be determined by that same exact thing. It's going to be x plus 1 minus the quadratic. And then we already know what that's going to end up to be from up there. So you have negative x squared plus x plus 2. And then this one's really easy because then when you drop that into the volume, so volume we're going to integrate from negative 1 to 2 because those were the bounds from the graph. And then it's just going to be this, we're just going to integrate that negative x squared plus x plus 2 with respect to x because it said that we are perpendicular to the x-axis. And then if you kind of did it like this, you already kind of know the answer here is going to be that 8.1 number. So that's how you have that. Okay. All right, so I will go ahead and do example 2 next. So we'll kind of scooch this up. In example 2, you kind of start out by graphing it, and hopefully you recognize that that is going to be a circle centered at the origin with a radius of 2 from pre-calculus, right? So that's a circle, 2 squared terms, identical coefficients. So you have that, and we're going to use the same graph for each of the examples. We start with equilateral triangles, and then we'll go to semicircles. So just graph that, circle centered at the origin with a radius of 2, kind of a quick sketch here, and then, my circle doesn't quite look perfect, but we get the idea. Another way to think of this, because when I go to integrate, we're going to need this. It says the cross sections are taken to the x-axis, so that means I need my equation to be a y equals equation. Well, that means I need to solve this for y. So that means y squared is 4 minus x squared. Take the square root. So y equals plus and minus the square root of 4 minus x squared. Keep in mind here, this is the positive square root. This top half gives you square root of 4 minus x squared here. And then this bottom part of the circle is negative square root of 4 minus x squared. And we talked about, graphing this kind of thing last class. So you've got this. And now it says find the volume if we're taking with equilateral triangles. So we're going to drop in equilateral triangles along this. So I don't know, if you dropped one in here and you dropped another one in here, right? You could tell that the equilateral triangle that you use over here is going to be smaller than the one that you have to use right here in area. So the idea is you stack all those equilateral triangles, you find the area of each one, you add them all together. So we need to first kind of figure out, well, what's the area of that? So before we could drop it into the volume formula, we find the area. So we know that area for an equilateral triangle, it's radical 3 over 4 times the base squared. So the base of each equilateral triangle in this is determined by doing this equation, which is the positive square root, minus this equation, which is the negative square root. So you got to kind of be a little tricky there. So it's going to be the positive 4 minus x squared. That's this top equation. So this minus this gives you that length right there. So that's minus the negative square root. So you've got a double negative. Watch your double negatives there. So that's going to turn to a plus. So you essentially have, so we've got radical 3 over 4. You essentially have 2 square root of 4 minus x squared. And that's squared. Now be very careful on your algebra here. Remember, when this is the quantity squared. So this thing squared means each piece is squared. So in other words, that's equivalent to 4 parentheses 4 minus x squared. Because the square and square roots kill each other, but this squared has to go on the 2 as well. So watch your algebra there. So you get to here. And then this 4 and this 4, well, they're going to kill each other off. So really, my area is represented by radical 3 times 4 minus x squared. That was a lot of work to get to there. I didn't even do the calculus part yet. Okay, so now I need to take this and put it into that volume formula. So remember, the volume, no pi this time, it's just going to be the integral from left to right. So our bounds here, we need to go from -2 to 2, of the area, which we already calculated over here. That's usually why I do my area in like a little side step. You could take this radical 3 and pop it out front. Can I fit it? Radical 3 there. And then 4 minus x squared dx. Okay? Then from there, you're going to integrate this. Okay? Add 1 to the exponent, divide by that number, etc. I'm kind of running out of room here. So I've got radical 3, and then you would say 4x, and then minus x cubed over 3, and evaluate that from -2 to 2. And then apply your fundamental theorem of calculus there. It's going to be a little bit of death by fractions, but I got 32 square root 3 over 3 is my final answer for there. So there's a couple examples. For the semicircles, it's going to be similar, but instead of an equilateral triangle, now it's going to be a semicircle that you're kind of trying to use as the cross-section. So you're going to have, that's not my best semicircle ever, but the idea is that you're going to have a whole bunch of these that you're going to stack up, okay? So for semicircles, the area for the semicircle is 1/2 pi r squared, okay? So for a semicircle, let's see, my r, that radius, okay, look at your picture, that radius is going to be this top curve, which is that square root 4 minus x squared, minus 0. So that actually is a little easier on this one. So you've got 1/2 pi, and then again, that radius is going to be changing because the semicircle that fits right here is going to be significantly smaller than the one that goes right across the middle. So that's going to be determined by the square root of 4 minus x squared minus 0, right? It's top minus bottom. And then squared. This one works out nice because those kind of kill each other off. So you've just got 4 minus x squared. And now that you can drop into the volume formula. So your volume, notice this volume is going to have a pi in it because it happened to ask me for a semicircle. The other ones did not have a pi in it. So we're going to integrate from -2 to 2. Okay, and we're going to have 1/2 pi, or pi over 2, which you could totally rewrite out front. And then that'll be 4 minus x squared dx. Okay, and then you can go ahead and pop that out front. You could integrate this, and it'll be a little bit of death by fractions, but I ended up with 16 pi over 3 when I was done. Okay, so hopefully that kind of explains a little bit of finding the volume by cross sections. Have a great day.